Well, welcome to our third Thursday webinar. I am Tom Sandry, and today we are going to be talking about resistance grounding system basics, a review of ungrounded, solidly grounded, high and low resistance grounded systems. All right, let's get started. Now, as the neutral point of an electrical supply system is often connected to earth ground, ground and neutral are closely related. Under certain conditions, a conductor used to connect to a system neutral is also used for grounding of equipment and structures. Current carried on a grounded conductor can result in objectionable and/or dangerous voltages appearing on equipment enclosures. So, the installation of grounded conductors and neutral conductors is carefully defined in electrical regulations. Where a neutral conductor is used also to connect equipment enclosures to earth, care must be taken that the neutral conductor never rises to a high voltage with respect to local ground. Let's start with the definition neutral. Neutral is a circuit conductor that normally carries current back to the source. The neutral is usually connected to earth or ground at the main electrical panel, street drop, or meter, and also at the final step-down transformer of the supply. That is for simple single-panel installations. For multiple panels, the situation is more complex. In the electrical trade, the conductor of a two-wire circuit connected to the supply neutral point and earth ground is referred to as the neutral. In a three-phase AC system, the neutral conductor is intended to have similar voltages to each of the other circuit conductors, but may carry very little current if the phases are balanced. The neutral wire is always assumed to be charged in an active circuit. Now, let's take a look at ground or earth. Ground or earth in a mains AC power electrical wiring system is a conductor that provides a low impedance path to the earth to prevent hazardous voltages from appearing on equipment, high voltage spikes. The term ground and earth are used synonymously here. Ground is more common in North American English, and earth is more common in British English. Under normal conditions, a grounded conductor does not carry current. Grounding is an integral path for home wiring also because it causes circuit breakers to trip more quickly, which is obviously safer. Adding new grounds requires a qualified electrician with information particular to a power company distribution region. Now, the term grounding is commonly used in the electrical industry to mean both equipment grounding or system grounding. Now, equipment grounding means the connection of earth ground to non-current carrying conductive materials such as a conduit, cable trays, junction boxes, enclosures, and motor frames. System grounding means the connection of earth ground to the neutral point of current carrying conductors, such as the neutral points of a circuit, a transformer, rotating machinery, or a system, either solidly or with a current limiting device. The figure shown illustrates the two types of grounding. As we can see, there are two types of grounding: equipment grounding for the safety of people, and system grounding for the protection of equipment. Now, both have features in common, and both are important for the proper operation of an electrical system. The National Electrical Code, or NEC, requires that all exposed metal on equipment and appliances be connected to an equipment grounding conductor. Under normal circumstances, no current flows in the equipment grounding conductor. The following example illustrates the purpose of the equipment grounding conductor. Now, the figure shown is a schematic of a device without an equipment grounding conductor connected to the metal chassis. The device is sitting on a non-conductive surface and therefore isolated from earth ground. The device is off, but a wire insulation fault has occurred before the switch. The metal chassis of the device is at an electrical potential of 120 volts with respect to ground. Now, since the switch is off and there is no path for fault current to flow, no current flows in the circuit. Hence, the circuit breaker will not trip and the fault will go undetected. Now, assume that someone is in contact with earth ground and they touch the metal chassis. There is now a path for current to flow, and it flows through the person. This is depicted in the illustration shown. For the circuit breaker to trip, the sum of the three resistances in the fault path must be less than 6 ohms. The internal resistance of the human body from any limb to any limb is approximately 500 ohms. In addition, the earth resistance may or may not be less than 6 ohms. The only requirement in the National Electrical Code, NEC, is that the resistance of the grounding electrode or ground rod be less than 25 ohms. Hence, even if the device is not isolated from ground or earth, the ground resistance may limit the fault current to below the trip point of the circuit breaker. Furthermore, there is usually considerable resistance between devices and earth ground. For example, the device may be sitting on a concrete slab. Now, the illustration shown here depicts the same device with an equipment grounding conductor connected to the metal chassis. The equipment grounding conductor provides a low resistance path for the fault current. If the equipment grounding conductor is 100 feet of copper wire, size AWG number 12, then it has a resistance of less than 0.2 ohms. If the fault resistance is less than 5.8 ohms, then more than 20 amps of fault current will flow in this circuit, and the circuit breaker will trip and de-energize the circuit. If the fault resistance is more than 5.8 ohms, the circuit breaker will not trip. However, the equipment grounding conductor will still hold the metal chassis to a safe voltage. More precisely, since the maximum fault current without the circuit breaker tripping is 20 amps, the maximum voltage at the metal chassis with respect to ground is 20 amps times the 0.2 ohms of resistance, which results in 4 volts. So what is a grounded system? It is a system in which at least one conductor or point, usually the middle wire or neutral point of a transformer or generator, is intentionally grounded, either solidly or through an impedance. This is the definition in IEEE Standard 142, 2007, paragraph 1.2.5. The types of system grounding normally used in industrial and commercial power systems are solidly grounded, low resistance grounded, high resistance grounding, and ungrounded systems. So what is the purpose of system grounding? Well, system grounding, or the intentional connection of a phase or neutral conductor to earth, is for the purpose of controlling the voltage to earth, or ground, within predictable limits. It also provides for a flow of current that will allow detection of an unwanted connection between system conductors and ground, and which may instigate operation of automatic devices to remove the source of voltage from conductors with such undesired connections to ground. The National Electrical Code prescribes certain system grounding connections that must be made to follow the code. The control of voltage to ground limits the voltage stress on the insulation of conductors so that installation performance can more readily be predicted. The control of voltage also allows reduction of shock hazards to persons who might encounter live conductors. So, let's now talk a little bit about faults and failures. A ground fault is an abnormal electrical current that causes a flow of current to earth. It can also be referred to as an earth fault. Now, before exploring the various system grounding methods, along with their pros and cons, we need to first understand the different types of faults that can occur in an electrical system. Faults can damage electrical equipment and facilities. They can drive up costs due to lost production time, and they can lead to employee injuries and even to fatalities. Basic types of faults include line to ground faults, a short circuit between one line and ground. Now, these failures represent the largest percentage of failures in an electrical system. Phase to phase or line to line faults, a short that develops between phases or lines in an electrical system. Now, these failures only account for a small percentage of all the failures in an electrical system. Three-phase faults. Faults which involve all the three phases are also known as symmetrical faults. Such types of faults remain balanced even after the fault. These faults make up a very tiny percentage of typical system failures and are often caused by human error. Failure to remove a grounding breaker, leaving ground clusters on systems, and lifting a truck bed or a man lift into an open wire system can cause these types of failures or faults. Arcing faults are intermittent failures between phases or phases to ground. They are discontinuous currents that alternately strike, extinguish, and then strike again. Okay, now that we have reviewed the different types of faults that can appear on electrical systems, it's time to provide an overview on the four main types of grounding systems you may encounter when you're in the field. Let's start with the ungrounded systems. The ungrounded circuit historically has been selected for those systems where service continuity is of primary concern. An ungrounded system is a system, circuit, or apparatus in which there is no intentional connection between the system conductors and earth. A system may still be considered ungrounded if there is a possible connection to earth ground through potential measuring devices or very high impedance devices. The term ungrounded is somewhat of a misnomer because in reality, there is a capacitive coupling to ground of the phase windings and conductors represented in blue on the schematic shown. In normal conditions, this distributed capacitance establishes a neutral reference that permits the phase conductors to be stressed only at line to neutral voltages. During ground fault conditions, the capacitive coupling provides a current path return to the unfaulted phases. This is defined as the charging current of a system. Through normal switching, like the operation of a breaker, or through restriking or intermittent ground faults, this charge can build up and cause transient overvoltages to build up. These overvoltages can cause insulation failures at other points than the original faulted point. This presents a high probability of a phase-to-phase fault and equipment damage. Now, many people are of the opinion that an ungrounded system is safer. This opinion says that since contact with a single phase does not complete a circuit, one should not get shocked. This is not the case because capacitive coupling to ground is present. In the example shown, a sustained ground fault occurs on a 480 volt Y connection. It could be a delta ungrounded system. Since the system is capacitive coupled to ground through a relatively high impedance, the unfaulted phase voltage is displaced above ground potential. The system will remain in this position until the fault is cleared or another phase breaks down to form a double line to ground fault. So, what are the advantages of an ungrounded system? Well, they offer a low value of current flow for line-to-line ground faults. They present no flash hazard to personnel for accidental line-to-ground faults. They assure continued operation of processes on the first occurrence of a line-to-ground fault. And they present a low probability of line-to-ground arcing fault escalating to phase-to-phase or three-phase faults. Now, unfortunately, this type of system also offers some big disadvantages. One major disadvantage to the ungrounded system is difficulty to locate line-to-ground faults. Finding the fault is a time-consuming process. For that reason, it's often done on weekends so that a company doesn't have to shut down its normal production processes. In addition, the fault must be located and repaired relatively quickly because if a second fault occurs, the fault acts like a phase-to-phase fault, extending the repair process. Now, also among disadvantages, it doesn't control transient over voltages. A second ground fault on another phase will result in a phase-to-phase short circuit. Alright, so how do we find the fault? Well, here we see ground fault detection lamps connected into the circuit. In a pre-fault, the lights are all on and have about a medium brightness. Now, voltage, AG would approximately be 277 volts. Voltage BG would be about 277 volts, and voltage CG would also be about 277 volts. Now, basically to find a ground fault on an ungrounded system, you'd have to turn off one load at a time until the lights return to normal. Now, obviously this can be very time-consuming and disruptive. So honestly, most facilities with ungrounded systems unfortunately don't bother finding ground faults. But as we see here, if a fault were to have occurred on A, in post-fault, the A phase lamp would be off and the others would be brighter. Now, basically the voltage from A to G would be 0. Voltage B to G would be about 480 volts, and voltage C to G would also be about 480 volts. Now, if this system is not built into, or if this fault detection lamps are not built into the system, commercially available on the market, there is a product from Protec Industries, and I did not intend to make this a commercial for Protec, but it is a test set that I am personally familiar with from the days that I worked at the Biddle company, which later became Avo or Megger. Now, the Model 7600 or Model 760 detects and locates accidental ground faults on both energized and de-energized power circuits, including single-phase, three-phase, and DC ungrounded systems. The 760 automatically determines which phase is grounded, and with a handheld portable pickup probe, the operator traces a signal tone to the exact point of the fault. The 760 is fully portable and can be used at any location in a distribution system. Due to the sensitivity of the pickup probe and adjustable volume control, the tracing signal can be heard as far as 5 feet from the conduit for easy tracing in difficult to reach areas. Okay. To learn more about the product, again, this is not intended to be a commercial for the Multitech product, but again, it is something that I am familiar with. To learn more about it, just simply Google search Multitech Industries Model 760. All right, let's move on to solidly grounded systems. Solidly grounded systems are commonly found in industrial and commercial power systems, where grounding conductors are connected to earth ground with no intentional added impedance in the circuit. In many cases, solid grounding, National Electrical Code Article 250-5, is mandated. In others, it is selected based on economics. The 480-277 volt system in Figure A is solidly grounded to permit 277 volt line to neutral loads such as lighting. For line to neutral loads to be applied, the neutral point of the Y connected source must be solidly grounded for the system to function properly and safely. If the system is not solidly grounded, the neutral point of the system would float with respect to ground as a function of load, subjecting the line to neutral loads to voltage unbalances and instability. The 120-208 volt Y system in Figure B must be solidly grounded to comply with the 1999 NEC Article 250-20, which says all systems with line to ground voltages of 150 volts or less, and for those systems with line to neutral loads. It is selected primarily where a lot of 120 volt line to neutral loads are present. Now, the 240-120 volt three-phase delta system shown in Figure C, typical of commercial power systems, must also be solidly grounded to comply with the NEC. The lowest line to ground voltage is less than 150 volts. A main secondary circuit breaker is a vital component required in this system, although it has no bearing in other grounding systems. This component is large in size because it has to carry the full load current of the transformer. Backup generators are frequently used in this type of grounding system in case a fault shuts down a production process. When this happens, the generator becomes solidly grounded. Now, consider a system having three phases, A, B, and C, shown in the figure. If the single ground fault occurs in phase A, the voltage of the phase becomes zero. However, the remaining two phases, B and C, will still have the same voltages as before. When the fault occurs in the system, in addition to the charging current, the power source also feeds the fault current. The flow of heavy fault current, I sub F, completely nullifies the effect of capacitive current at the fault, so no arcing ground or overvoltages. Due to the flow of high fault current, protective relaying is possible. All right, now let's look at the advantages and the disadvantages of the solidly grounded system. Among the advantages, good control of transient overvoltage from neutral to ground. It allows users to easily locate faults, and they can supply line to neutral loads. But among the disadvantages, they pose severe arc flash hazards, requires the purchase and installation of a main breaker, unplanned interruption of production processes in the event of a fault, potential for severe equipment damage during a fault, high values of fault current, likely escalation of single-phase faults to three-phase faults, and creates problems on the primary system. All right, now let's take a look at resistive grounding methods. The reason for limiting the current by resistive grounding may be one or more of the following. 1. To reduce burning and melting effects in faulted electrical equipment, such as switchgear, transformers, cables, and rotating machines. 2. To reduce mechanical stresses in circuits and apparatus carrying fault currents. 3. To reduce electrical shock hazards to personnel caused by stray ground fault currents in the ground return path. 4. To reduce the arc blast or flash hazard to personnel who may have accidentally caused or who happen to be in close proximity to the ground fault. 5. To reduce the momentary line voltage dip occasioned by the occurrence and clearing of a ground fault. And 6. To secure control of transient overvoltages while at the same time avoiding the shutdown of a faulty circuit on the occurrence of the first ground fault. This would apply to a high resistance grounding system. Resistive grounding may be either of two classes, a high resistance or low resistance, distinguished by the magnitude of ground fault current permitted to flow. Now, although there are recognized standards for the levels of ground fault current that define these two classes, in practice there is a clear difference. High resistance grounding typically uses ground fault current levels of 10 amps or less, although some specialized systems at voltages in the 15 kV class may have higher ground fault current levels. Now, low resistance grounding typically uses ground fault current levels of at least 100 amps, with currents in the 200 to 1000 amp range being more usual. Now, both types are designed to limit transient overvoltages to safe levels, within 250% of normal. However, the high resistance method usually does not require immediate clearing of a ground fault, since the fault current is limited to a very low level. This low level must be at least equal to the system total capacitance to ground charging current. The protection scheme associated with high resistance grounding is usually detection and alarm rather than immediate trip out. In general, the use of high resistive grounding on systems where the line to ground fault exceeds 10 amps should be avoided because of the damage potential of an arcing current larger than 10 amps in a confined space. Alright, let's look first at low resistance. Low resistance grounding has been selected for large electrical systems where there is a high investment in capital equipment or prolonged loss of service of equipment has a significant economic impact. A resistor is connected from the system neutral point to ground and generally sized to permit only 100 to about 1000 amps of ground fault current to flow. Enough current must flow so that protective devices can detect the faulted circuit and trip it offline, but not so much current as to create major damage at the fault point. Damage to motors and other rotating equipment is also limited. Since the grounding impedance is in the form of resistance, any transient overvoltages are quickly damped out and the whole transient overvoltage phenomena is no longer applicable. This method is employed on 2400 volt and 4160 volt circuits. The low resistance method has the advantage of immediate and selective clearing of the grounded circuit, but requires that the maximum ground fault current be large enough to positively actuate the applied ground fault relay. Alright, now let's look at the high resistance ground. High resistance grounding systems are commonly used in plants and mills where continued operation of processes is paramount in the event of a fault. It is a system grounding technique mainly used in low voltage systems, most common in 480 and 600 volt systems. This arrangement means that a certain resistance has been intentionally put between the neutral point of the system ground and earth ground. If the system does not have a neutral point, it is necessary to create one artificially. A few methods are available to accomplish this, such as a zigzag transformer or a Y-delta transformer. The resistance is chosen such that its magnitude is less than the magnitude of the system charging capacitance. That means it is set up so that the charging current will be less than the ground return current through the neutral resistor. A 480 volt line-to-line system will usually have charging currents of up to 2 amps. This means the grounding resistance should allow a ground return current with a magnitude over the magnitude of the charging current. This system is to make sure that the ground return current will flow through the resistor and not charge the distributed capacitances, thus causing transient overvoltages, possible restrikes, and potential phase-to-phase faults. It allows the system to stay in service, but it is highly recommended to try and correct the fault as soon as possible. During ground fault conditions, the voltage to ground on the two unfaulted phases is equal to the line-to-line voltage. The equipment rating has to be rated at 173% of their line-to-neutral voltages. Now let's take a look at the schematic for tap values and corresponding terminal numbers. The resistor tap setting will determine the amount of ground return current that a system will allow and or whether the HRG will function properly. Improper resistor tap setting may result in equipment damage or malfunction. The tap points are brought to a terminal block in the control section. If the tap jumper is omitted, the resistor assembly will be at its lowest current rating, 1 amp for a 1 amp to 5 amp assembly, as shown in the example. For high current levels, connect the jumper from its base point to the tap terminal marked with the required current level. Refer to the schematic for tap values and corresponding terminal numbers. Now, this example comes with 5 resistor settings. 5 amp tap, which has 57 ohms, a 4 amp tap, which has 69.5 ohms, 3 amp tap, 89.5 ohms, 2 amp, which has 139.5 ohms, and a 1 amp tap, which has 264.5 ohms. There are 2 important factors that should be considered when choosing which resistor setting to use in a system. 1. The charging current of a system. And 2. The amount of ground return current through the neutral resistor that should be allowed on the system. It is rather important to consider these factors in this order because the capacitive charging current will provide the minimum amount of ground return current that should be led on the system to make the HRG effective. That in turn relates to the maximum grounding resistance that can be chosen. Note, the ground return current to be allowed on the system should be higher than the charging current of a system. In other words, the grounding resistor value to be chosen should be lower than the capacitive coupling to ground. The reason behind choosing a grounding resistor value that is lower than the charging capacitive coupling is so that in case of a ground fault, the return path of the ground current will be assumed to flow through the grounding resistor and not through the alternate capacitive path. Note, for most systems, a resistor tap setting of 5 amps will exceed the capacitive charging current of the system, yet still prevent equipment damage. Now, determining the capacitive charging current. There are different methods to determine the capacitive charging current of a system, but they all prove to be tedious and or impractical. It is advisable to use the industry-accepted method of estimating the charging current instead of calculating and/or measuring it. It is important to note that the capacitive charging current of a system is the current that flows toward the unfaulted phases during a ground fault. This current is different from the leakage current that flows to ground from the phases during normal operation. The leakage current, typically of very small magnitude, will continuously flow through insulation. Estimating the charging current. This is the preferred method for determining the charging current of a system. IEEE Standard 141, IEEE recommended practice for electrical power distribution for industrial plants, recommends a resistance value that limits the maximum ground current between 5 amps and 10 amps for high resistance ground systems. It also recommends for high resistance grounding to be used only in systems of 5 kV or lower, charging currents of 5.5 amps or lower, and never in 15 kV systems. Now, a way to estimate the capacitive charging current for low voltage systems is as follows. A 480 volt system. 0.5 amps per 1000 kVA or 0.5 amps per set of surge capacitors used. All right, now let's talk a little bit about neutral grounding resistor calculations, for instance, in a low resistive grounding system. The neutral grounding resistor will limit the ground fault to a maximum of 100 to 1000 amps. Zero sequence current transformers and ground fault relays will detect the fault and trip at 5 to 20% of the maximum ground fault current. The resistor is generally rated for 10 seconds with a maximum temperature rise of about 760 degrees Celsius. The maximum ground fault current allowed by the resistor has to be large enough to positively actuate the applied ground fault relay. 200 to 400 amp rated neutral grounding resistors are generally used in 6.9 kV to 34.5 kV systems. 100 to 400 amp rated neutral grounding resistors are generally used in 2.4 to 4.16 kV systems. Once the current rating is determined, the resistance or ohmic values of the resistor is calculated by dividing the line to neutral voltage by the current rating. For an example, a 41.6 system neutral grounding resistor rated at 400 amps. The line to neutral voltage will be 4.16 kV divided by the square root of 3, which equals 2,400 volts. The required resistance will be 2400 divided by 400, or 6 ohms of resistance. All right, now let's look at neutral grounding resistor calculations for a high resistance ground. The neutral grounding resistor will limit the ground fault to a maximum of 5 to 10 amps. Zero sequence current transformers and ground fault relays will detect the fault and alarm at 10 to 20% of the maximum ground fault current. The resistor is rated for continuous duty with a maximum temperature rise of about 375 degrees Celsius. The maximum ground fault current allowed by the resistor must exceed the total capacitance to ground charging current of the system and the vector sum of the system charging current, plus the resistor current shall not exceed 8 amps. Once the current rating is determined, the resistance or ohmic value of the resistor is calculated by dividing the line to neutral voltage by the current rating. For example, a 480 volt system neutral grounding resistor rated at 5 amps. The line to neutral voltage will be 480 divided by square root of 3, which equals 277 volts. The required resistance will be 277 divided by 5, or 55.4 ohms. All right, let's take a look now at advantages and disadvantages of resistance grounding. Well, among the advantages, it limits ground fault currents to low levels, reduces electric shock hazards, controls transient overvoltages, reduces the mechanical stress in circuits and equipment, and maintains continuity of service, and offers possible arc flash risk reduction. But among the disadvantages, ground faults may be left on the system for an extended period of time, and there is an inability to service line to neutral loads. All right, now let's take a look at low resistance grounding versus high resistance grounding. Low resistance grounding limits the phase to ground currents to greater than or equal to 100 amps, whereas in high resistance grounding, it limits phase to ground currents to less than or equal to 10 amps. In LRG, reduces arcing current and, to some extent, limits arc flash hazards associated with phase to ground arcing current conditions only. In HRG, reduces arcing current and essentially eliminates arc flash hazards associated with phase to ground arcing current conditions only. In LRG, it may limit the mechanical damage and thermal damage to shorted transformers and rotating machinery windings. In HRG, it will eliminate the mechanical damage and may limit thermal damage to shorted transformers and rotating machinery windings. In LRG, it does not prevent operation of overcurrent devices. In HRG, it prevents operation of overcurrent devices until the fault can be located, when only one phase faults to ground. In LRG, does not require a ground fault detection system. However, in HRG, it requires a ground fault detection system to notify the facility engineer that a ground fault condition has occurred. In LRG, it may be utilized on medium or high voltage systems. Matter of fact, GE offers low resistive grounding systems up to 72,000 volts line to line. In HRG, it may be utilized on low voltage systems or medium voltage systems up to 5 kV. IEEE Standard 141 states that high resistance grounding should be restricted to 5 kV class or lower systems with charging currents of about 5.5 amps or less, and should not be attempted on 15 kV systems unless proper grounding relaying is employed. All right, in LRG, conductor insulation and surge arresters must be rated based on the line-to-line voltage. Phase to neutral loads must be served through an isolation transformer. In HRG, conductor insulation and surge arresters must be rated on the line-to-line voltage. Phase-to-phase loads must be served through an isolation transformer. And further system grounding method comparisons. Let's look at all four. Under characteristics, allows continuation of process upon occurrence of the first ground fault. Yes for an HRG, no for an LRG, no for solidly grounded, and yes for an ungrounded. Controls transient overvoltages. Yes on an HRG, yes on an LRG, yes on a solidly grounded, and no in an ungrounded system. Eliminates arc flashes. yes in an HRG, reduces but does not eliminate in an LRG, not in a solidly grounded, and yes in an ungrounded. Quick discovery of ground fault location. Not on an HRG, yes in an LRG, and yes in a solidly grounded, and difficult to find ground faults in an ungrounded system. Limits thermal damage to equipment. Yes in an HRG, yes in an LRG. No, in a solidly grounded, you're taking the full impact of the maximum fault current. And yes in an ungrounded system. And ability to serve line to neutral loads. No in an HRG, no in an LRG, yes in a solidly grounded, and no in an ungrounded system. And that concludes our webinar on resistive grounding systems, or system grounding basics. Again, I'd like to take this time to thank everybody for joining us every month on our third Thursday webinars. Again, I truly hope that this is a benefit to everybody and you are enjoying these webinars. We are going to keep the lines open, obviously, because now we are in the questions and answers time period. So without further ado, let's get to those questions.